Well, today, there are two presentations. Liam and then Emily and Abby are going to present. We'll get started on that right away. That means everybody else is presenting on Friday. We do have the room from the start of the class time till 3:05 on Friday, so it's about an hour and a half time period. And I think there's 10 more presentations, so it's about 9 minutes per presentation on Friday, so it's a big day to get that. So I'm glad a couple are getting done at this time. After the presentations, there'll be some time we can do questions for review and talk about things. Without further ado, Liam signed up to go first, so we'll start with that. Okay. And for all of them, I'll just be taking some notes, writing down some things to keep track, and then likely ask a question.
Hello. So I did my presentation on something called hazard functions, and a little bit of background / inspiration for why I decided to choose this topic was I was doing some soldering on electrical components, and I had a big box of old fuses. And I tried one fuse and it immediately blew out. I tried another fuse and it immediately blew out. And I was getting really frustrated, and so I was thinking about how long do fuses normally last, if there's some sort of governing rule for these kind of things, and I got into looking at survival analysis and hazard functions. So this is the most common model if you look up reliability, especially when you're talking about products. The top one is the so-called bathtub curve, which is the general distribution that survival of objects in terms of failure rate have. So in the beginning, there's a decreasing failure rate, and then it stays relatively constant. It increases as time goes on. But there are a couple other models that can work for it. So random failure rates versus an earlier failure rate with decreasing, or failure rates that significantly increase over time. So the actual hazard function I chose to examine is this symbolically. In words, this says if you have a random variable capital T that's distributed as some probability distribution, this gives you the rate of change of the probability that T will survive to T plus delta, given that it survived up to time T already. And so with this, you can analyze the rate of change of the survival of objects, given the probability distributions that they're distributed as. Some of the most common models for survival rates are the exponential model, a Weibull model, or a logistic model. So if we go back to here, the early infant mortality failure, that could be modeled as an exponential variable with the strictly decreasing, very high at the beginning, lower later, and the other ones work as well. So you all know exponential distributions, and so depending on the lambda parameter, it adjusts how likely that it will continue surviving. The steeper it is, the more likely it's going to fail sooner. And the hazard for an exponential model, ooh, this is upside down, that's supposed to just be lambda, sorry. The hazard for an exponential model is actually just lambda. So there's a constant rate, and every single time t, the failure chance is lambda. So this is good. This is why exponential models are nice, if there's just a truly random chance for it to fail at every single time step t. The next one, which is a very convenient distribution, is called a Weibull distribution, which, as you can see here, it's got a lot of different shapes to it, and especially with the k parameter, you can adjust the distribution. So for k less than 1, you get a very steep decline with a huge probability of failure rate early, and it decreases over time. If k is equal to 1, then you just have a standard exponential distribution, which is pretty convenient. And then for t greater than 1, you have a couple of opportunities for the failure rate to increase over time. And so if we look at corresponding hazard function, the hazard function for it, so as you can see, the straight line would be a Weibull distribution with k greater than 1, such that the probability that the chance of failure increases consistently. The straight line is the exponential model, where it's just a continuous at every single time step t, there's a failure rate of lambda, and then the decreasing one, which you can use to model things like earlier failure of products or infant mortality or things like that. Another interesting distribution is the logistic distribution, commonly used throughout probability and statistics. And logistic distribution is nice because it's kind of like a normal distribution, but with more heavily weighted tails. And so you can use this to, if you're not as sure that it's going to fall within the standard normal model. And with this, you can model the failure rate pretty nicely. And even more conveniently, the failure, the hazard function for this, while it might look a little bit strange, it is actually just the 1 over the scale parameter times the cumulative probability density function, so that the probability that you will survive to a time t plus delta, given you survive up to a time t, is just the scale parameter, 1 over the scale parameter times the cumulative probability function. So you get these nice S-shaped curves, and you can use this to model a lot of nice survival analyses and lifetime and all of that. My scale's a little bit off, but the blue line curves up eventually. It's just a wider scale factor. And so that's pretty much what I looked at. Just different models of hazard. Yeah.
Here's a couple of follow-up questions. So these are really popular models for survival. So you'd want to know parameters, right?
Yeah.
So what would happen with data? For instance, with different people surviving a certain, or objects, the circuits surviving a certain time, you get a bunch of failures at certain times. What I haven't seen the write-up, but what would be
The write-up goes into some more details about
about
that.
estimation.
But, about the estimation, doing inference based on actual failure times, and also like fitting your model using chi-square.
So can we see one of the probability density functions, like, so instead of the hazard, just going back 1 or something? Yeah, so that'd be like the probability function. So if you get a bunch of TIs, right, what would you do?
So if you had a bunch of TIs, you can, it's a little bit difficult to predict because it's a 2-parameter distribution, but you can either assume one of them is fixed, or you can use most of the inference procedures that we've used to try to determine actual parameters based on data.
Yeah, so you get a bunch of T's, right? You'd have each of those functions multiplied together, and it's not as pretty as those other things, taking a log and taking a derivative. You have to use some numerical methods, but you're right. But estimate mu, which is kind of the middle of each of those curves, and S some type of spread, and it does, yeah, it can be a little more spread out than normal. So you get those, and you can predict. Right? So two kind of interesting things that come up with this is censoring. Right? So in a lot of medical studies, they will start, how long does it take until somebody dies or gets better, or until their blood chemistry changes after they're on treatments. And some people will do the 3-year study period and not have any event. So we don't know when they're going to fail. So you get kind of you get a cutoff for this, and then there's different ways of estimating the survival, taking into account that there's a probability that you would be beyond observation time. So yeah, so probably the person who got the first, there's a new thing, International Award in Statistics. And the first person who got it was Sir what's his name, Cox. But anyway, there's a Cox proportional hazards model, right? it says there's a baseline hazard, and then the hazard changes depending on your characteristics. Are you male, female? What's your age? So those can be fixed, or they can vary over time. And so that's a key, right? So this is kind of the starting point for a lot of engineering, but also survival in medicine. So
Yeah, there's a lot of more complicated survival models that I briefly glanced at and decided it was slightly out of the scope of this project.
something like I say Weibull, but some people could say Weeble. I guess if you're English or British, you'll say it one way or the other. Right? It's like an exponential raised to a power, and there's some others that are kind of transformations of exponential. So this could have some probability theory where you get between one and the other. So
The Weeble also interpolates between exponential and Rayleigh, which is cool.
yeah. Any questions? So, well, thank you again. So. The second one is a duo. Abby and Emily on the data set. This one.
Alright, so we did something completely different, and we decided to look at a data set on victim versus perpetrator murders in the US. So our paper focused on murders and non-negligent manslaughter between the years 1980 and 2014, and we analyzed different variables between the victim versus perpetrator, being age, sex, race, and then we also looked at the relationship between the two. Like for example, if they're boyfriend girlfriend, if it was a stranger, if it was unknown, and we also looked at the state that the murder took place in. And the goal was to show that there was a relationship between some of these variables.
So our data came from the Murder Accountability Project, which is the most complete database of homicides in the U.S. This is because it included, FBI Supplementary Homicide Report and the Freedom of Information Act data, which includes murders that were not reported to the justice system, which was kind of cool. We cleaned the data. There were some that seemed like typos, so there's an age that was 998, which obviously no one is 998 years old. And we took out data that said that there were children under 14 who committed murders, although not impossible, probably unlikely, and rare. So.
Yeah, we assumed those would be typos too. Did they really mean to click 1, or did they mean to click 19, or something like that? So we decided to get that out so it wouldn't skew it dramatically. So some of our data that we found was, so this is the first table we have, and this is the counts for victim sex, and there's a total of 638,000 victims. About 77% were males, and 22% females, and 0.1 with unknown sex. And then table 2 gives the perpetrator sex, and with the same amount of perpetrators as victims. And there is 62% that were males, 7.6 females, and 29.8 being unknown. And although the unknown number seems really high, it kind of makes sense because a lot of the crimes that were in this database were unsolved. And when the crime's not solved, that means you don't know who the perpetrator is. And so if you don't know the perpetrator, you obviously don't know their sex. So that number makes sense to us.
So the next table we have perpetrator sex versus victim sex. And this did not include the unknowns. You can see that there were a lot of unknowns, about 2.35 times, or unsolved, about 2.35 times the number of solved crimes. So if we look at this, we did a chi-square test, and at the 0.05 significance level, we found that our p-value was smaller than that. So it was not independent, and they do depend on one another, which makes sense.
So these data sets are about their age. So this table 7 gives age range of victims, with 4.17% of victims being between the ages of 0 and 9, 12% being between 10 and 19, 33% between 20 and 29, 21% between 30 and 39, 12% between 40 and 49, and so on and so on. And then here are the counts for the perpetrator ages, and we found that the highest correlation by a couple of thousand was 20 to 29-year-old being the perpetrator, and the same age range for the victims. So we found that that was like the highest count, is those ages.
So then here are just some counts of the victims perpetrated by race. You can see that the most was with black and white for both victim and perpetrator. So you just kind of get an idea of like how we're looking at. See some total counts.
Okay, so part of what we found, we kind of wrapped it up into this because we had over 50 tables, and we weren't going to present all of them today. So pretty much what we found was that, like I said before, 29.8% of perpetrators were sex unknown, and we found that most perpetrators, we had a higher percentage of unknown, and that's because if you don't know who the perpetrator is, again, you don't know any of their information. We had over 190,000 cases that were unsolved. The mean victim age was 35, while the mean perpetrator age was 20 years old. And the relationship that occurs between the perpetrator and victim, the most is acquaintance, which makes up 19% of the data, and followed by stranger at 15%. And we found this kind of weird because we thought maybe you always hear about the cases of the husband killing the wife or anything, but that wasn't, those were very little, less than 5%. And then we also found that nearly 50% of the victims were white, and close behind was black victims, which made up 46%. And Asian Pacific Islanders and Native Americans / Alaska Natives were a little less than 2% of the data.
So similar to that, the perpetrators were also white and black were pretty similar. White was a little more, both about 35% or 34%. And Asian and Pacific Islander and Native American and Alaska Native put together made up a little more than 1%, so it was pretty small. When we looked at them by state, the most was in Texas, New York, and Florida, and also Vermont was a very small number, along with Montana, New Hampshire, Wyoming, Maine, and North and South Dakota. And South Dakota had a really small number, it was only 308, which that was interesting. But also there's a smaller population there with a
That's
larger,
35 years, right?
Yeah,
So Dana's
really small. Yeah. And then we found that male victims and male perpetrators were the most by a couple of thousand, so that shows that there's probably a pretty high correlation between that. And then when we did the odds ratio test, we found there was a big spike in 1991. We looked into trying to see if there was new laws or something like that. We didn't really see much.
Yeah,
so.
I'll talk about it. Yeah, next slide. Alright, so what we came to conclusion is that there's a lot of crimes unsolved, and this makes sense because with the justice system, you have to prove beyond reasonable doubt that the perpetrator actually committed the crime. So this doesn't say that there's no suspects for all these unsolved cases, but unless they can prove it, then they can't be filed into this major database. And we did some research on what happened in 1991, and I found a couple of papers talking about it. And I guess that year is when abortion was legalized, it's the decline of crack, there was more police, and there was increased incarceration, and these four things decreased crime significantly, and it's been on a steady decrease since. And obviously with any data set it could be more accurate. For our states one, we were thinking we'd do a percentage per capita. That way it's a fair comparison between the states, because it's not fair to compare Vermont to New York. New York has millions more people, so it makes sense that they have more murders there. Again, also bias within which cases are solved. We hear a lot that if it has to do with drugs, alcohol, prostitution, or homeless people, those cases usually get put on the back burner and aren't set precedent. So if we had all of those numbers and all those cases be solved, that would probably change our data significantly. And also there's some data that's missing. This is the most accurate database that has all murder, not all murders, has the most murders in it, but the FBI isn't required to put all these into a document, which is why there's no document under the Federal Bureau of Investigation made. So that's why this private site did it, but there's some missing data. Obviously they can't catch everyone because not everyone's required to report. And also, like we said in the beginning, there's human error. 998 doesn't make sense for an age. It's probably it was probably considered like they didn't know the age of the Type 998. But like also if the perpetrator's 2, did they really need 2 or did they need like 22? So that could also drastically change our data as well. But yeah.
Good. Any questions about?
Did you know that the reason Florida, you hear about it in the newspaper so often, is because they've got like a really strong Freedom of Information Act, and almost all police cases are available to the press.
I did not know that.
So that's one of the reasons that Florida is probably up there.
No,
is
that's
that
interesting. Yeah, that could also
information is very
affect it,
easy
yeah.
to access.
Yeah.
Yeah, no, I mean, people think that there's a unified federal statistical system for all data, but there's not. There's no unified crime data. And so
Yeah.
that's a real hindrance, right?
Yeah.
Somebody's putting crimes in one state, they don't necessarily have records available to the next state over, even county to county basis. And so it's really difficult. And if there's a situation where there's like an accident, like a car crash, and people are dying, dead, the police don't necessarily record, was there alcohol at the scene, or was there any other factors, and that just doesn't enter the database because there's so much else going on, so it's quite different. But the 1991 one is kind of interesting. So there was an odds ratio.
Yeah,
for
so we
that.
did the odds ratio, and it went from like 0.8 and then to 1.
Yeah, so this
Like
was an
once-
odds ratio for, in terms of the sex. And
Yes,
the, right,
yeah.
so you'd have the sex of the victim, male or female, and was it committed by a male or female
Yeah.
perpetrator. So you have an odds that was a male, female versus
Yeah.
male victim, and then, well,
Yeah,
based
male
on
versus
what the
male.
perpetrator, right? So there was some change
Yes.
over time, and so, abortion was legalized with Roe v. Wade in '74, but this was '91 was during Clinton's first administration.
Yeah, that's what there's a whole paper. We cited him in our paper about like how all of these working together
Yeah.
created like the decline.
Yeah, they were, I can remember this a little bit, but there was a big push to put more police on the streets,
Yeah.
get more, so that was part of it. Federal sentencing guidelines were there, so that would have locked people up longer, yeah.
I know with the abortion thing, I don't know if they're in the same paper, but, the argument with abortion is basically that that's around the time when, people who, since abortion was legalized, those babies that basically weren't born into homes where maybe they weren't as, taken care of, or
Yeah.
weren't able to support them, went into foster care or whatever, basically those children did not grow up to be in a sort of raised place where they could have been more likely to be criminals, and that
Yeah.
is why it dropped. That's why it's
Yeah, that's
correlated.
Yeah, that's what I was reading. Like since it happened in 1970, then the babies that would have been born
Yeah, so
those years.
17, 20 years
Yeah.
later,
Yeah.
there's some impact.
Yeah.
Basically, there's evidence that children in neglected homes end up becoming,
Mhm.
are more likely to become criminals, and so with abortion, less of those children were born.
Yeah. And going off that, we're interested to see what the next 34 years with technology enhancing all the time, if there will be a database that is required for everyone. And that being said, even more variables could be added. It'd be interesting to see where the justice system goes.
Right. Okay. Great. So then on Friday, we have a whole series of other presentations, and so it'll maybe feel a little rushed to go through. We'll have 9 minutes. I'll kind of keep it phone, try to keep us on time for that. Right. And so we have some time in the second half of class now for questions, for looking at some review for things. Homework 9 has been returned. I'll finish grading homework 10 shortly, and when that's done, I'll probably send a message saying it's done and leave it outside my door so you could pick it up. I'll be in on Thursday for office hours, so that would be a time to talk. So, so homework, homework 9 and 10 solutions are posted if you want to look at those. Homework 9 had the tail end of hypothesis testing with some power, and then some things with discrete data, and well, and then 10 had some discrete data and some Bayes. So a couple things in there. I'll post some other problems. We won't really have time to talk about them on Friday due to that, but if you want to look at them, you can come into office hours. We could talk other times on Friday. If you have questions or want to send emails on the weekend, I'll just see what, Monday's the start of the exam period, so it's kind of hard to have. We kind of leave that open for because some of you will have full exams and be busy those days and so on. But are there any particular questions or topics you want to talk out or do a short review of that you can think of at this point? Studying, looking over the homework and the solutions, the previous exams, and I'll post some studies the last couple class periods. We talked a little bit about kind of the scope of the exams, so you focus on that. You do get a sheet of paper, right? So you can write on both sides with formulas and notes. No particular questions. No. So, one topic we didn't exactly cover that's listed in some of the learning objectives is something called decision theory. And it's related to hypothesis testing. And it's something that in the previous iterations of this class, either we've gotten kind of a day or part of a day, it's a broader topic related to hypothesis testing that particularly comes up in economics or business related to things. And the nature of this one, in hypothesis testing, we set up, we have some probability distribution, f of x, with some parameter. And then we have a null hypothesis that says maybe it's this parameter or an alternative that it's not that. And in hypothesis testing, we're going to gather data, x1, x2, right up to xn, and then we want to make a decision. Right? And so we're either going to reject H0 and conclude that the alternative is best. Right? Maybe that's given a value of 1. And, or, we don't reject. Right? Maybe that's given a value to 0. So these are kind of the possible decisions that we can possibly make. And decision theory is related to this in that we set up a rule for deciding something based on our data. And it elaborates how we're making that decision by putting more information about costs there. Primarily where we've had our costs are type 1 and type 2 errors, where we only want to make a mistake and reject this 5% of the time, right? We don't want to make, if the null hypothesis really is true, we don't want to make a decision more than 5% of the time or so. Let's get out of that. We also considered power. We don't want to fail to reject if the alternative is some alternative really is true. So there's kind of a cost for those. And there's a trade-off, right? If we make it harder to reject and make this 0.001, very, very small error rate here, well, we usually don't get much power because we have to have such an extreme result to reject the null that the alternative almost, unless it's really a big difference, right, happens. So there's this trade-off between that. And so in decision theory, they set up a series of actions, right, such as, reject the null, don't reject null. Null. Other actions can tell you as to use the data in a certain way to estimate a parameter, right? It could tell you to use the maximum likelihood estimate. It could use the unbiased estimate. It could use method of moments, right? It could set up that type of rule to do. Or you should do a Bayes estimate, report the posterior mean, right? So the actions can tell you what to do with data. And so X, we're going to get some data in this, and we have some parameter theta. And so we consider decision rules. D of X is going to be a decision rule. And we've done this for hypothesis testing. Right? We've said, where's the rejection region? Right? And so if our X bar is too far away, positive or negative from theta 0, right, then we say we reject. And we choose how far away based on the standard error and our alpha level. Right? So for instance, in our hypothesis testing, if the mean is supposed to be some mu sub 0, and the alternative is that it's not this, and we choose alpha, 5% type 1 error, we can reject the null hypothesis if X bar, is greater than, well, let's do it just, let's do it two-sided. If it's greater than, the mu sub 0 plus a t-value 0.95, a minus 1, like 0.975, sorry. Or we have to cut it in half for two-sided, times s over the square root of n, right? Or X bar is less than, right, 0.975, a minus 1 s over the square root of n. So that's a decision rule. If it's outside of those intervals, we reject. We don't expect to make any more error than that. And we would like to have large powers. We generally choose a larger sample size, so s over the square root of n is not so big, so that if mu sub a, the alternative really is a certain distance away, we're very likely to be far enough away to do that. Right? Decision theory kind of elaborates this in just a little bit. And we're not going to go into details, so I'm not testing you on it or asking problems. But we set up a loss function. What do we lose by making a certain decision? What could we lose? And that's a function of the parameter and the data. Right? So theta is the parameter. It's either theta 0 or theta a. And then we're going to have our decision. What do we lose if we make the wrong decision? Well, it could either be 0 or 1, like you make an error or you don't. But you could put a price on that error. Right? So we talked about kind of the context sometimes of type 1, type 2 errors. If it's a medical study and you decide that no, there's no real benefit of a drug, when there really is a benefit, if you're rejecting the hypothesis and there's no real benefit, but you think there is a benefit, then you're going to advocate people do something that doesn't really help them. It's going to cost them money. Right? Maybe has some side effects too, so that's not good. But if there really is a difference, but you fail to prove it, right, then your cost is you're not giving somebody a medical advantage. Right? And so there's those costs. If in economics or some decision, you might put dollar amounts on those things. Yeah.
But even for medical, how do you choose which one's worth it?
Which one's which? So usually usually this would be something like no benefit.
Yeah.
Is of a new therapy. We might express it as two different means, mu1 minus mu2, or they're equal, the difference is 0. So the null is usually no benefit. Right? And so if we see a big enough observed difference, favoring the new therapy, you would say, oh, we need to change to the new one. And so type 1 error would be would be rejecting the null hypothesis is no benefit when it's actually 0, right? So you should stay on. You shouldn't change. The correct decision would be no change, no new expensive drug because it doesn't really help. But if you, yeah, that's the type 1 error. That context. So there's loss, right? This will depend on the data and that. So you either get a correct decision or not, depending on what the true value of theta is. But the way decision rules get compared is taking the expected value of those. So the risk related to a decision rule is mathematically is an expectation. And so it's interesting to try and introduce this, but it does add a little probability theory. So it's nice to have, you know, a week or two to do more of this, right? And so these are more thinking about the alpha and beta error levels. Right? So it kind of averages over the possible data. So in our things about hypothesis testing, we talk about how do procedures perform, how does decision rules perform, and that's the alpha and beta that are there. Now, if you had one way of deciding on something that gave you smaller error levels for both, you know, that'd be great. You would do it. Usually that means you add sample size. You know, keep alpha the same, add sample size to make beta smaller. But except for that change, usually there's a trade-off. Right? For type 1 error, you know, alpha 0.05, well, you would like to have small error rate. So we would like this one, but as alpha goes down, beta usually goes up. You know.
Beta goes down.
Well, so if this one goes down, then larger beta. So that means smaller power. Because the picture we have to illustrate power, right, that we've used several times is this type of picture, where here's the null hypothesis and here's the alternative. And we're going to reject the null hypothesis. This is sampling distributions for x bar. We're going to reject the null hypothesis two-sided, you know, if we're out, you know, here. Right? Those are the rejection regions out here. And these are set up so that we have little areas under the curve, right? Little alphas here. And then power is the area under this, you know, curve. It would include this area down here, but I want to not completely overwrite it. You know, power. So if you make alpha smaller, you got to push this out, which makes these red tail areas smaller, which is good. But it's going to make the blue area go smaller, and we don't like that. So there's a trade-off between these things. And so every choice of alpha and its corresponding beta is a decision rule. So which decision rule do you like to have? Right? It's not necessarily a correct decision, but there's a couple of things that get done. Right? Which decision rule, which protocol for using your data should you use? Which decision rule? Hypothesis testing usually takes a 5% error rate or so for the type 1 error, and then tries to get adequate sample size to get power up. That's usually how that goes. But you know, in other contexts, you could look at costs or time or dollars to do that trade-off. One approach is called minimax. And so over the different values of the parameters that could happen, right? And parameters, you know, in this case there's 2 alternatives in the hypothesis testing. But it could be, you know, what is p? What is the mean? Right? It could be really continuous type of thing. Right? And so this is minimize, you know, the maximum risk. So as a math function, you're minimizing over the different decision rules the maximum risk that you could have under each decision rule, where theta is from its different options. And here's this capital theta type thing. Right? So there's a risk associated with a certain decision for a parameter, and for each decision there's some maximum risk. But then if you can look at the maximum risk over all the parameters for each decision rule, and then choose the one where you're going to get the least risk, right? So what's an example of where this would apply? So when I worked at George Washington University, I would take the subway in from Rockville out here, and we would go past DuPont. Subway with DuPont Circle, and here's Farragut North Station, and then here's Metro Center. But then you had to change lines and go over to Foggy Bottom, and George Washington University was over here, right? So the decision rule could be, where do we get off the train? Right, this is about, it's not quite a mile walk, but you can walk it, right, there. And so where do I get off the train? The decisions then are, where do you get off? Here, here, or here, right? The parameter is going to be, which one's going to, how much time is each decision going to take, right? Once I get here, it's just walking time. Here, it's travel time plus walking. And then it's travel time change travel time to get there, right? So those are the costs. There's some uncertainty about the train, right? The data you would get is essentially how are things going, right? Up there. Sometimes the train is just sailing along, 3 minutes each station, and going. And sometimes you end up waiting someplace for a train to clear ahead of you, and so on. Right, so what's minimizing the maximum risk? Right. So I often thought about it as getting off at one of these two places and walking, because I didn't want to deal with the change, right? Because although this could be faster if everything works, right, and that would be the correct decision under good conditions, it could be a very bad decision, right? Because you could end up waiting here in the middle for things to change, or you can get here and that line isn't working, right? So you could have a very bad decision, very bad outcome there, and that seemed to me, averaging over the possibilities, to generally have a lot of risk, right? No matter whether things are working well or not, right? So getting off here, you kind of know what it is, right? You're just going to walk, wait for a few stop signs, stop lights and things, and not have that pause. So minimize the maximum risk can be done. The other way that this goes is, a Bayesian, right, we have these different risk functions, which for each decision rule and parameter values, we have some idea of what the risk, what would be the average loss, the average loss there. Well, if you're Bayesian, you think about this unknown parameter as a random variable, and you put a prior distribution on it. And given the data, or kind of given x, you can get a posterior distribution. So the decision theory kind of then combines what we did with Bayes with costs associated with decisions, with losses. Right? So Bayes would choose the decision rule to minimize the posterior loss, or the expected loss under this posterior distribution. So I'm going to write this down. Not as much of this will, kind of given D, but this kind of expectation means the average loss given a posterior distribution of the data. Right? We mentioned one result kind of tied to this. Right? One application of this that we did see was called a Neyman-Pearson lemma, which said that for comparing two simple hypotheses, the most powerful test at a certain alpha level, a certain significance level, is the likelihood ratio test. It ends up being like a posterior mean Bayes comparison under a certain kind of equal prior distribution. So anyway, we didn't cover it explicitly and go into another round of formulas and things. The key ideas are in there in hypothesis testing, and thinking about, how does a Bayesian learn from data and update to get information about the prior. It's also kind of incorporated there, looking at likelihood ratio, what values of the parameters are most likely for the data. So it kind of ties things together, and it'd be nice to have a little more time to do that. But it's always been kind of a secondary topic in this course, in a way, to talking about hypothesis testing and figuring out things with power and seeing what a likelihood ratio is a little bit more. So that's where we've got our focus. And so you can kind of ignore the details of this one, because we're not going to test on this, but kind of reviewed a little bit of the setup of hypothesis testing. So there is some relevant for doing it. Right? And if you go on in economics or business, it might be very well that more decision theoretic framework gets used. So. But anyway, any questions? So the others of you have, presentations. If you can submit the project papers on Friday, that would be great. But I know that there's a lot of stuff going on, so you might get a draft of the paper and finish up the presentation and get that ready, and need just a little more time, either later that day or over the weekend to finish up the paper. But the more that can come in, the better it is for me grading, and it also frees up your time to study for other things. Pencil is nice because then I can make comments on it. But, if it's not coming in on Friday, then electronic should work out. There's yours. Thank you. Why?
Good question.
Okay.
So they just gave me today. I'll call them. Okay.
How you doing? I don't know what this is. So this is recognize that.
Okay.
I'm reading it.
Is it there?
Yep, so this is, but
Oh, so
when
this-
I go to type in
So-
mean of SAT reading, it says the variable isn't there.
Okay, so you'd either have to attach the data set, right, or refer to that column within that. So if you, right, so that's not there. So if you attach this thing, right, so right now it doesn't know where to look. It doesn't
Okay.
even know to look at these names here. It's just looking at a higher level. Right?
Oh, I see.
So if you attach, oops. Caps locks maybe. Shift ST underscore. There it is. Yeah. If you attach that thing, now try the mean SAT max. So there's a missing.
Because I have that first column there, which I can easily just or delete. Make sure there's no. Yeah.
So that can either be changed in the. There's no total or anything. So
Okay, so I can just delete that.
you delete that row.
I can just re-import it
Right.
and then do that attach.
You might detach what? And so, so let's.
Because I already have that.
It's already in
Yeah.
there, right?
Okay,
So let me just.
detach and then reattach.
Right, and this is, you can see, so there's different objects, search in there, so, you know, you can attach. This doesn't get rid of them both, because I don't know where they are. So
Okay.
now that none of them are there, and if you reattach, so you just attach it, it will be the latest one.
Which will be
Yep.
project raw dot. Do I need the dot?
No,
CSV?
no, it'll be,
Okay.
it's just like that one up there, right? So now your mean should work and not have that last.
Cool. Perfect. Cool. So I wasn't really going to get into these three. I'm just going to focus on the numerical values of the SAT, of the math, and what they now call the EBRW, which is basically just reading and writing combined together, and then the cumulative GPA.
Okay.
Just going to look at those.
Right. So talking a little bit, you know, if you're using a correlation or regression models,
Or
you know, talk a little bit about that and how you do estimate, you know, least squares estimation. So a couple paragraphs, let's talk about estimation, because this course is kind of focused on estimation and inputs, but then an applied data analysis.
Yeah.
Did those data come from St. Michael?
Yeah, that actually came from the registrar.
Right.
They gave me but I guess that could be another, I guess that can be talked about in discussion about.
Oh, yeah, sure.
How that's like, maybe it's not actually random, maybe that's like the first, 300 that they actually had.
Maybe, yeah, you don't know.
And they're just, they like, how could they actually randomly draw, 300?
Some would, or,
Yeah.
you know.
But yeah, it's so that's real data from the registrar, current data too. That's the most recent that they have available. And then and then I was gonna, who was it? That site that I also linked with it had data on St. Mike's aggregated for like through 50 years or
Yeah.
something. So they had the actual means
Right.
over those times, and
Yeah.
so I was gonna compare those and stuff like that. But
Okay,
cool. All right, so yeah, I'm probably gonna submit online Friday afternoon,
okay.
because I also have an econometrics project
Uh-huh.
due Friday, and my clean data for senior cent due tomorrow night. So I got quite a bit.
Yeah, a lot coming back here, so.
Yeah, tell me about it.
Did you have a good time in Colorado?
Yeah, it was awesome.
Yeah.
We got super fortunate. For skiing,
Yeah.
you want snow, but
Right.
you don't want it fresh. So you want hard snow,
Ah.
which we only had one heavy snow day of
Ah.
like, I guess bad training,
Uh-huh.
because training courses in powder is not ideal.
Yeah.
So we only had one of those days when we were out there. But it was sweet. Our coach is super happy. Everybody's skiing pretty well so far. So
Good.
first race is on Saturday. Yeah,
That's
right.
Right in the middle of finals, right?
Yep. Yeah. So
Yeah.
yeah, I got another busy weekend coming up. So I'm racing. The races are Saturday, Sunday over in Sunny River, so 6.5 hours away
Oh,
in Maine.
wow. Yeah.
But I'm only doing Saturday, and I'm driving down to Gillette that night to go see my little cousin. He's playing in the state championship football.
Ah, cool.
And then driving to a funeral Sunday morning, and then driving back here.
Oh my goodness.
Yeah, so got a busy weekend.
Yeah. Right. And so our exam's on Tuesday
Mm-hmm.
for that. So you're in good standing for this, but we want some review and time to put together a sheet.
I thought our exam was on Friday.
I think ours is Tuesday.
Okay, I might be mixing it up. So yeah, I go Monday, Tuesday, Friday. So I could just be mixing up my econometrics exam that's on Friday or something.
Right.
But yeah.
Here's the,
Yeah, that's
we could look at the.
yeah, I can just look at it later. But
There we go. So, save mark. They don't ever go through St. Michael's to try to find anything. So ours, Monday, Wednesday, Friday, 1:30, we're Tuesday.
okay, cool. All right. And then, so then when was my? Oh, okay. So I'm going back to back on Tuesday.
When is yours?
So I'm going 8:30 to 11 on Tuesday, and then 11:30 to 2.
Oh, this is your other class?
Yeah, econometrics. All right, there we go. All right, thank you.
Yep.